All right. So what I want to do today is I want to continue our discussions. So this is Math 341, Stat 341, lecture, I think, 31. And what I'm going to do is I'm going to give a version of a talk I've given numerous times over the years on Benford's law of digit bias. So if you've never heard of Benford's law, it is a very interesting tool which can often be used to indicate that something nefarious is going on. But of course, there can be other explanations for it, as we will discuss as well. So it's a really nice application of probability and statistics. It cuts across many different disciplines. Again, the goal for the last week or so of lectures is to talk to you about what can you do now that you've taken probability, and to give you a little bit of a sense of some of the research opportunities over the summer. So I will be leading some projects related to this in summer 2022. All right. So the motivating question is, imagine you have a nice set of data, maybe Fibonacci numbers, and yes, for me, that's a nice set of data, stock prices, street addresses, and so on and so on. And you could ask, what is the probability of observing various first digits? So the natural guess is 10%. Why is the natural guess 10%? 10 digits. And then why do you immediately correct? Well, you correct. Yeah, you're not going to start off with 0, because we write numbers in scientific notation. So if the number is 0.0053, you would write it as 5.3 times 10 to the negative 3. So the only number that has a leading digit of 0 is 0. And so frequently we just remove all the zeros from the data set that we're looking at. And so you might expect 11% of the time to see each digit. It turns out for a lot of different data sets, you have a pretty much stable result. Doesn't really matter what you look at. You basically see about 30% of the time a first digit of 1, decreasing monotonically down to about 4.6% of the time having a first digit of 9. And we'll see later today a couple of explanations for why this is true in various settings. So we actually know enough to prove stuff like this. So let's just see a couple of examples. So if you look at Fibonacci numbers, Twitter users by number of followers, most common iPhone passcodes. I will talk about how you get that data later. And then distances of stars from the Earth. You see remarkable agreement with this Benfordness. Now, it's not perfect. And to some extent, the more data sets you look at and the more averaging you do, the better it is to Benford. Certain things fit Benford much better than others. Fibonacci numbers are one of the best things you can find. It's a pure Benford process. The other ones, there's going to be some slight issues. Okay. So what I want to do today is I want to explain explicitly what is Benford's law, where does it come from, talk about some examples and applications. And it's nice that the math that you're doing can actually be used to discover things. I will sketch some of the proofs, and as time permits, I'll discuss some of the open problems. All right, so the first is you always have to be careful what you're doing. A math test indicating fraud is not proof of fraud. Unlikely events or alternate reasons can go on. So I actually emailed Scott Adams for permission to use this, and he was kind enough to grant. So your travel expenses are rejected because all of your meal costs are round numbers. You're a liar or worse. I decide what to order based on what totals to a round number after 15% tip. That's worse. So there can be alternative explanations for what's going on. The way you can look at something like Benford's law is if you see large deviations, it could be an indication that something is going on. And if you have finite resources, this could be a good area to investigate. You might find something going on here. It does not mean that something nefarious is going on. All right. So there's lots of different places in the world where we will see Benfordness. We'll see them in recurrence relations, which are discrete versions of differential equations. So this might explain why it occurs in so many different natural phenomena. Special functions, iterates of power exponential rational maps, a lot of hierarchical Bayesian models, a lot of financial data. The financial data is extremely valuable. When people are trying to decide, have numbers been cooked in certain reports? You can often do a Benford test to see, can you trust the data? And a lot of times in some of the companies that have been found to, let's say, have some issues with their books, or some countries that have had some issues with their reports, it has been discovered that a Benford analysis does indicate that this is worth looking at. And I'll give some examples of that in a little bit. Some other applications are analyzing round-off errors. In terms of working with a computer, there's going to be issues on how things are rounded off. determining optimal ways to store numbers. This is a little bit less important now than it was 50 years ago, just because technology is going so rapidly that the storage crunches aren't quite there. I remember the first computer I programmed on, I had 16 kilobytes of memory, and that was with the expansion. And so you had to squeeze every little bit you could out of these systems. A real big one is detecting text and image fraud and your data integrity issues. And so I will be discussing this in great length in a little bit. All right, so let's just do the general theory of Benford's law first. All right, so for many data sets, the probability of observing a first digit of D base B is the log base B of D plus 1 over D. So base 10, that means about 30% of the time, you're going to start off with the first digit of 1. Do you believe that this is a probability distribution? Yeah, I'm given that I'm lecturing on it, I've probably done the checks. What two things should we check? Adds up to 1. Well, what's nice is the sum of the logs is the log of the product. So for once, we're actually going in the opposite direction. And if you look at them, oh, I've got D plus 1 over D. So I've got 2 over 1 times 3 over 2 times 4 over 3. And when you take the product, everything is going to cancel. It's going to be like a telescoping, and you'll be left with 10 over 1. So it does work out very nicely. And it's clearly non-negative. Okay. So a little background material. How many of you have ever taken a class in abstract algebra? I actually cannot raise my hand now. I never took abstract algebra. I've taught it, but have never actually taken it. So we fortunately don't need to know too much. So we say A equals B mod C if A minus B is an integer times C. So anybody who's ever looked at a clock, if it's 9 o'clock now, what time is it in 4 hours? 1, right? So 9 plus 4 does not equal 1, but it does on a 12-hour clock, because every time you hit 12, you reset. And so we really care about a clock with 1 hour. In abstract algebra, you care often about clocks with prime hours. Here we care about a clock with 1 hour. And so we look at basically just the fractional part. So 4.5 is the same as 0.5 mod 1. All right, the next is the significand. Given any number, I can write it in scientific notation. The significand is going to be some number between 1 and 10. I'm working base 10. And then I have times 10 to the k, where k is an integer. So if I have a number like 2021, it would be 2.021 times 10 cubed. Anybody know anything like Planck's constant off the top of their head? That would be another number where you would have a huge negative exponent. Yeah. We don't really care about the exponents because all we care about is the first digit, or maybe the first 2 digits. And so when you write something in scientific notation, you can just focus on the part of the number you care about. This is why this is so important. So 2 numbers are going to have the same leading digits if and only if they have the same significance. And this is pretty much exactly what you would expect. All the 10 to the k does is it just pads zeros. It just moves the decimal point. It's not going to change what the leading digits are. So the log of x base 10 is the same as the log of the significand base 10 plus an integer k. So if I only care about the significand, instead of studying the number, it actually turns out to be easier to study the log of the number, base 10, and then take the fractional part of that. So this is very similar to whenever you have a product, you should always be thinking of taking a logarithm. We are going to be taking a logarithm here. We have a product looking in the background. I'm going to just chop away the integer part. Normally, if you throw away the integer part, this makes a difference. If you have your bank balance and I just chop off the integer part and leave you with the fractional part, this is not a good day for most of us. That should be noticeable, right? But if I only care about the significand, if I take the log base 10 first and then throw things away, it's not going to change the distribution of the leading digits. What's really lurking in the background is the following. So 2 numbers have the same logarithms base 10 if and only if they have the same first digits. And that's because the difference is going to be that k coming from the 10 to the k. Why is this useful? Well, what's lurking in the background is Fourier analysis and complex analysis. So hopefully you've seen e to the 2 pi ix, or e to the I theta is cosine theta plus I sine theta. Does this sound vaguely familiar? At least some people. You might have seen the de Moivre's theorem. cosine theta plus I sine theta, looking at powers. If not, it's okay. But e to the 2 pi I u is e to the 2 pi I u mod 1. So every time I increase u by 1, I end up increasing the exponent by 2 pi I, so I don't really change things. Another way of looking at it is e to the 2 pi I u is cosine 2 pi u plus I sine 2 pi u. Well, if I have cosine 2 pi u and I increase u by 1, inside the cosine, the argument goes up by 2 pi. Oh, well, if I increase the argument of cosine by 2 pi, I don't change its value. Wow, we have a function which doesn't care about your integer part. These exponentials only care about the fractional part of u. That's precisely what we want to study. So this is the deep reason why we want to switch to Fourier analysis. And again, you want to identify what's going to be a useful tool for your problem. What do I know? I want to chop off the integer part. Well, normally you can't just chop off the integer part. That's going to affect things. But when we do the analysis here, it makes no difference if I include or not include the integer part. Okay, so the next concept we need is equidistribution. This is essentially uniformly distributed. So we say a sequence yn is equidistributed mod 1 if the percent of time that it lands in an interval AB goes to B minus A. So again, if you take the interval 0, 1, let's say yn lives in 0, 1. So clearly, if I take AB to be 0, 1, then 100% of the time it's going to be there. If AB has length 1/2, I would expect about half the time in the limit my terms to land in that interval. If I have AB equaling 1/3 in length, I would expect about 1/3 of the time. So essentially, the fraction of the time you fall in the subinterval is equal to the length of the interval. And there are a lot of sequences that are equidistributed, and they're going to really be responsible for the Benfordness. So there's a nice theorem. Professor Silva and I will slightly disagree as to, is this an ergodic theorem or is this a number theory result? But if beta is an irrational number, then if you look at n beta, so beta, 2 beta, 3 beta, 4 beta, and you look at their fractional parts, that's equidistributed mod 1. Okay, what class did you see this in? Real, okay. So when you look at something like this, you always want to ask yourself, how important is this condition? Imagine beta is rational. Can somebody give me a reasonable rational number? 1/2. So let's look at n times 1/2 mod 1. So we would have 1/2, then we would have 1, which is the same as 0, then 1/2, then 0. And so in fact, if I give you any rational number for beta, if beta is 1/5, you would cycle through 1/5, 2/5, 3/5. So clearly you're going to just cycle. Now, in some sense, you are spaced evenly. So it does kind of look equidistributed, but it's going to be very much focused in certain places. So if we take 1/2, if I choose an interval AB that doesn't include 0 or 1/2, then the probability is going to be 0. So we clearly know that n beta is not going to be equidistributed if beta is rational. The deep result is that it is true if beta is irrational. It turns out you can even quantify how quickly it becomes equidistributed. It turns out this is related to how irrational a number is, and we have ways of determining how irrational a number is. In some sense, the most irrational, anybody want to guess the most irrational of all the irrationals? No, but not a bad guess. Because if it's not something that you've seen, you basically have no chance in hell. So pi is a good one to try. Cube root of 2 is a good one to try, but no. Nope. Square root of 2, though, is the closest. It's actually 1 plus root 5 over 2. It's the golden mean. The golden mean is the most irrational. And if there's time or interest later, I'll explain why the golden mean is the most irrational. So as an example, the log of 2 base 10 or the log of 1 plus root 5 over 2 are irrational numbers. And just to give a proof, let's prove that the log of 2 is irrational, base 10. So if it was rational, then I could write this as p over q for some integers. So 2 equals 10 to the p over q. Well, 10 is just 2 times 5. So it's breaking up a little bit. So we'd go 2 to the q minus p is 5 to the p. Well, the only way 2 to a power can equal 5 to a power is if they're both to the 0 power. which would mean P has to be 0 and Q minus P has to be 0. So Q is 0. So I've got, so yeah. So it's a nice exercise, prove that the log of the golden mean base 10 is also irrational. All right, I had to choose a specific number just to have the slides. I chose the square root of pi. Square root of pi is irrational. So by our result, n root pi mod 1 should be equidistributed. I have 10 data points. Does this look good to you? I've got a histogram of how often it is in each interval of length 110. So what do you think? I'm sorry? Yeah, but I'm saying for 10 data points, does this look pretty good? Yeah, come on. I've got 8 bins that have exactly 1 bin that has 2, 1 bin that has 0. If I gave you something that every bin had 1, you might think I'm cooking the books. So this looks like good real world data. It's a little bit messy. All right, but you're right, let's look at something a little bit larger. Let's look at 100. Let's look at 1,000. I'm seeing the eye doctor later. So maybe by sometime next week, I'll be able to see the actual differences. If you look at the very top as to, there are little bits of fluctuations. So it really does look like, n times root pi mod 1 is becoming equidistributed. Okay, why do we care about this? Well, the fundamental equivalence is if we want to prove a data set is Benford, then the original set xi is Benford, if and only if the logarithms base b mod 1 are equidistributed. So rather than looking at the original data set, it's enough to look at the logarithms mod 1. Why is this the case? Well, I write my number as a significant times 10 to the k. When I take the logarithm and I look at it mod 1, the k vanishes and I just have the log of the significant. And so now, here's the scale from 0 to 1. This is looking at the logarithms. Here's 1 to 10 is looking at the significant. How do you have a significant with first digit of 1? Well, I need all of the numbers such that when I exponentiate, I have a first digit of 1. So the largest number, or the smallest number that doesn't exponentiate to a first digit of 1 is going to be, I would have a significant of 2. So everything from 0 to the log of 2 base 10 exponentiates to having a first digit of 1. Everything from the log of 2 base 10 to the log of 3 base 10 exponentiates to having a first digit of 2. And if it's easier to just view it vertically rather than horizontally, these are the numbers that are going to exponentiate to a first digit of 1. And so explicitly, the probability of a leading digit of d is it's the log of d plus 1 minus the log of d. Because the percent of time that I land in here, because it's equidistributed, is going to just be the length of the interval. And so when you exponentiate, that's where you get the d plus 1 over d. All right. So again, we've talked about Rubik's cubes before. It's the power of finding the right perspective, the power of looking at the algebra the right way. Rather than looking at the original numbers, you should look at their logarithms and chop off the integers. And again, just like you should not be doing logarithms when you're dealing with a third grader in multiplication, if you're talking about batting averages or something like that, or stock prices, you don't really do something like this. But in terms of doing the analysis, this is the way to look at the data. All right. So I'm going to first prove that 2 to the n is Benford base 10. So, again, there's a limit to how much data I can show. Well, I'll do that later. So we know the log of 2 base 10 is irrational, right? We just proved that. So if I look at the data x n is 2 to the n, we know 2 to the n is Benford if and only if its logs mod 1 are equidistributed. Well, the log of 2 to the n is just n log 2. And we know the log of 2 is irrational, so n log 2 is Benford. We could even quantify precisely how quickly Benfordness sets in. Let's do a little bit more interesting. Let's do the Fibonacci numbers of Benford base 10. So the Fibonacci satisfy a recurrence relation. We've seen this before. Recurrence relations, it's really great to know how to solve stuff like this. So an plus 1 is an plus an minus 1. So we can solve it, the method of divine inspiration. You might recognize these slides. Guess an is r to the n. We plug that in, we get r squared equals r plus 1. And now when we try to solve, we see the roots of r equals 1 plus or minus root 5 over 2. And what's going on right now is we have a linear equation. If I take two solutions and add them, it's still a solution. If I take a solution and I rescale it, I multiply by 5 or 7, it's still a solution. So the general solution is of the form C1R1 to the n plus C2R2 to the n. And then I just choose C1 and C2 to satisfy the initial conditions, and you get Benet's formula. What's wonderful about that is the second factor, 1 minus root 5 over 2, is less than 1 in absolute value. So as you take n to be enormous, that number goes to 0. So the nth Fibonacci number is essentially just 1 over root 5 golden mean to the n. So if I want to then look at, is the Fibonacci number, or the Fibonacci numbers Benford, I just have to say, well, is n log of this equidistributed? The log of 1 over root 5 is just a constant shift. It's not going to matter. The log of 1 plus root 5 over 2 base 10 is irrational, so we're in business. The only thing we have to be careful about is we just have to do a little bookkeeping as to how much can that change the leading digit. Well, if you think about how small this is, it's going to be extremely hard to change the leading digit. The only way it's going to work is if you have a number that's like, blah, 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 long number of digits, 0.999999999. It sounds like Batman coming down. And then that's just enough to push it up. And even in that case, your number would have to be a bunch of 9s in the integer part so that when it's pushed up, it eventually propagates all the way to the first digit. So you can see it's going to be a real challenge to change the leading digit. So with a little bit of bookkeeping, you can make it work. It turns out most linear recurrences are Benford. And this is, again, one of the reasons why it's so prevalent. Not everyone is. Now, we talked about the doubling before. AN is 2 to the n. That's a linear recurrence relation. AN plus 1 is 2AN. If I tweak it a little bit, though, and do 2AN minus AN minus 1, this is not going to be Benford. And again, this one was chosen very, very carefully. If I take A0 and A1 to be 1, you'll get every single term in the sequence is 1. If I take A0 to be 0, A1 to be 1, I get 0, 1, 2, 3, 4, 5, 6, 7. What's going on is when you try to solve the recurrence relation, and we make this guess with R's, you get, there's a double root, and it's R equals 1. Well, the log of 1 base 10, that's 0. Okay, that's where things are breaking down. Let's look at some data. So let's look at powers of 2 to the n. There's a limit to how many I can show on the board. I'm going to look at the first 60, but I'm only going to display the first 30 because the numbers are getting quite big. I report how often I get digits 1 through 9. I report the observed percentages and the Benford probabilities. So you can see, 1, I should get about 30% of the time. I get about 30% of the time. 2, I should get about 17.6%. I get 20%. So when you look at this, do you think the data looks good? Do you think it supports Benford? Or do you have concerns about any part of it? 7 and 8? So is 7 and 8 the ones you're most concerned about? Is it?
Generally, other than like 7, 8 more than all.
Yeah, which one do you think is the most concerning? And again, there's more than one right answer. Probably 7. I found 9 to be the most concerning just because of the relative size difference between them. But again, we have 60 data points. 60 data points is not large. So who here is a computer scientist? All right. How many megabytes are in a gigabyte? It's 1,024. Now, when you think about it, mega and giga, these are supposed to be, 1,000. Why is there 1,024 rather than 1,000? Is it because the computer scientists just don't understand Greek and Latin? Everything is base 2. 1024 is 2 to the 10. So 2 to the 10 is 1024, which is almost 10 cubed. Imagine a slightly different world where 2 to the 10 actually equaled 10 cubed. then if you consider the doubling, every time you increase n by 10, you would exactly return to where you started, padded with 3 zeros. So in that world, you would not get Benford. You would just keep cycling among those first 10 numbers. So that's why if you look at this, it's not a coincidence I've written it like this. If you take this row, 64, 65536, and so on, the first digit is the same as we keep going. We actually haven't seen any of these come up yet with a new digit. Eventually, 7s and 9s are going to have to merge, but it takes a while for them to appear. Again, think Rubik's Cube, think what is the right way to write the data. Rather than flooding you with theorems to memorize, I really want to just take the time and talk, how should you look at things? And when you look at this, we're not seeing anything appear. And the reason is because 2 to the 10 is almost 10 cubed. And so it could take a while for the Benfordness to really settle in. The other thing is we have so few numbers that should have a leading digit of 7, 8, or 9 that sometimes what you do is you combine them. You want to have at least a 5% probability in each bin. All right, so this just barely makes it. But maybe you want to combine 8 and 9 together. Well, if you combine 8 and 9 together, that would be about 0.1, very close to 0.1. And when you do combinations like that, things are looking much better. So again, you have to be a little bit careful how you look at the data. And is it really indicating that something is going wrong? Or is it just suggesting something that you might want to study? All right, so we haven't talked too much about chi-squared goodness of fit tests, but we have talked about chi-squared random variables. So what you can do is you can look at the observed minus predicted. And if your theory is correct, if your conjecture is correct, then observed minus predicted should be small. What's the problem with looking at a statistic like observed minus predicted? I'm sorry? Okay, but what's bad about looking at summing, say, observed minus predicted as we sum over everything? Yeah, you could cancel, right? It's sign. We never want to look at something like observed minus predicted. So what should we look at? Observed minus predicted squared, hell no to the absolute value. The absolute value is a pain. So the chi-squared statistic comes from looking at observed minus predicted squared, and then you divide by predicted. That's a good normalization. The smaller the chi-squared value is, the better fit you have, the better job your theory is doing at describing. And so again, this is something that you can look up. We can talk about this if people are interested. But it comes down to the fact that if you square a normal random variable, what do you get when you square a normal random variable? Say standard normal. The square of a standard normal is what? So the square of a standard normal is a chi-squared random variable with 1 degree of freedom. So if you have a bunch of things, if you have a bunch of errors that you think are normally distributed, if you normalize appropriately and square and you sum them, then you get a chi-squared random variable. And that's where the whole theory of the chi-squared goodness of fit test comes from. And again, this is a way for us to quickly review chi-squared random variables. And so this should really be a chi-squared random variable with 8 degrees of freedom. Why 8? Well, we have 9 digits, but if I know what the errors are for the first 8, the 9th is forced on me. And so about 95% of the time, you should have a value of 15.5 or lower if your theory is doing a good job predicting your data. And so I chose 3 completely non-random numbers. I chose the Euler-Mastroianni constant gamma, which you might have seen if you look at the harmonic series. I chose E and I chose pi. And I reported on their chi-squared values. And then if you've ever seen the Sesame Street game, one of these things is not like the other. One of these things just doesn't belong. When you look at this, which one is basically screaming at you? Pi. Something is going on with pi. Now, at first, it looks like, okay, well, maybe pi just started off bad, but pi got better. And then it started getting worse again, and got better. But in fact, even some of the other ones, they started getting better, and then they got worse again. So, what's going on? So let's look more closely at pi. And I'm going to look at pi, and I'm going to look at e. So I'm going to look at the leading digits of pi to the n and e to the n. And I'm going to plot on the x-axis, the largest n I look at. So I'm looking at all n from 1 to 200 and 400, etc. And the y-axis is going to be the log of the chi-squared. Why am I applying the log of the chi-squared? Because there's so much order of magnitude difference, I want to be able to see it all on one piece of paper. So again, this is another chance to praise logarithms. I want to be able to see this. So again, you're a data scientist now. Somebody gives you this plot. What do you think of when you see it?
Gross.
I'm sorry?
Gross.
Gross. Do you think pi and e are behaving similarly? There's definitely some differences between them, but I think there are some similarities. Yes. Generally. Yeah, there's a general decreasing going on. When you look at the red, a certain word should be popping into your mind. Periodic. Anybody want to estimate the period? Okay, can you be more specific as to how much under 200? I don't know if I can read.
175.
Okay, 175. So if you look at basically from here to this low point, that's 200, 100, 150. Yeah, it looks about right in the middle, about 175. All right. Who here doesn't mind being outed as a math geek? All right. Can you give me digits of pi? Yeah, you don't even know the first digit. Okay. Raise your hand if you can do 1 digit of pi. 4 digits of pi. 10 digits of pi. Okay. Pi squared. Wait, you stopped? What is this? Once you did pi, why didn't you move on to pi squared? So I love this next slide. Pi to the 175 is 1.0028 times 10 to the 87. What that means is a large integer power of pi is almost 10 to an integer. Imagine you were in a world where pi to the 175 was exactly equal to 10 to the 87. In that world, what would happen? Well, every time we increase by 175, we would return to where we start, and it would be completely periodic. And that is why you have something like this. Looking at this data actually suggests that pi to the 175 should be close to a power of 10. It's amazing what you can see from a picture. Okay, I'm going to skip the next couple of slides. This is some advanced results and some new theory I did with some students a few years ago, where we looked at more general recurrence relations, where rather than constant coefficients, we allowed the coefficients to vary. So I'm going to skip all of that and talk about why Benford's law. And so some of these slides you will have seen. So imagine you have a long street with houses numbered from 1 to L. Depending on what L is, you're going to see a very different distribution of leading digits. So if L is 199, you've just gone through 100 houses with a first digit of 1. If L is 999, you've just gone through about 800 houses where the first digit is not 1. So depending on what L is, you can have a great difference in the probability of a first digit being 1. And so if we plot, you can see this oscillation. Instead of plotting it like this, though, what might make the plot a little bit better to look at? What could we do? Yeah, take logs. Always take logs. And so if we take logs, you can see, as you expect, a much nicer pattern. So imagine we have a lot of streets of different lengths, and we amalgamate. So typically, the more you amalgamate, the more things get smoothed out. And so imagine, let's do it very simply. We have 1,000 streets. Each street is from 1 to 10,000. And we just pull houses from that. Well, if we do that, we're going to just get the uniform distribution. Okay. Now let's make it more interesting. We have 1,000 streets. Each street is from 1 to a random number uniformly chosen from 1 to 10,000. So different streets have different lengths now. And now when we pull our data from that, we can see it's no longer uniform. It's not Benford yet. The blue line is the Benford theory, but it's getting closer. If we do another iteration, we randomly choose a number from 1 to 10,000, and then randomly choose a number from 1 to that, you can see it's looking a lot closer to Benford. If we do it one more time again, even better. And you can prove all of this mathematically, that the more you iterate, the more randomization happens, the more things become nice. So, again, the main things we need is the area under a curve is the probability, the mean is the average value, variance is spread out, independence means knowledge of one does not give any information about knowledge of another. We've done the central limit theorem numerous times. It's not bad to review this. This is one of the key takeaways of the course. So the density, we've seen this numerous times. We look at standardized normal variables. So what we do is we subtract off n times the mean, and we divide by sigma root n. So we now have an object that has mean 0, variance 1, and this converges to being normally distributed. So I've shown you these pictures before. Here's taking just a uniform random variable adjusted to have mean 0, variance 1. And you see, it's not horrible, but it's not given well by a Gaussian. If I take the sum of 2, this is essentially like rolling 2 fair die, but the continuous analog, it's actually not terrible in terms of just how good the Gaussian does, which is a little surprising. But when you have everything normalized appropriately, it's not that far off from a Gaussian. By the time we do 4 of them, it's pretty close. At 8 of them, it's extremely close. And then I think we've seen the slide before of just how bad it is to explicitly write down the densities. As an exercise, do this calculation. And by do this calculation, I mean train some computer software package like Mathematica to do this calculation. Or take, if you're a JA, have one of your Fosh do it or something like that, right? Try to do what happens if you have 8. I'll make that extra credit, to actually write down what it is for 8. And if you can't do 8, do 6, okay? And just see how bad it is. And this should hopefully just drive home why we care so much about the central limit theorem. We don't want to work with this. We want to basically say, look, see how close that is to a Gaussian? Let's just say to hell with it. Let's just approximate it with a Gaussian and move on. All right. So when you look at this, I am plotting a normal distribution with mean 0, variance sigma squared, but I'm plotting it mod 1. So what that means is when I look at the probability, everything from 0 to 0.1 or 1 to 1.1 or 2 to 2.1 and so on and so on and so on is collapsed and comes down here between 0 and 0.1. So when you look at the uniform distribution, that's the solid gold line. The green line is the normal with a variance of 0.01. If the variance is 0.01, what's the standard deviation? 0.1. So for a standard normal, about how many standard deviations do you have to go to capture almost all the probability? About 2 standard deviations. 1.96, I think, gives you the 95%. 2.54 or 2.56 gives you 99%, something like that. Look, if I go over 2 standard deviations over here from 0 above, and then 1 is the same as 0 because I'm doing things in the mod 1 world, going to the left, 0.2 there is really just what would be going on the side over here. You can see that's most of the probability. So this picture is at least consistent with the fact that most of the mass of the normal is going to be between negative 0.2 and positive 0.2. And the claim is that as the standard deviation goes to infinity, a normal with standard deviation sigma converges, when you look at it mod 1, to a uniform. Well, if you think about it, if the normal has larger and larger standard deviation, it's looking flatter and flatter and flatter on these intervals of length 1. And so when you amalgamate, it should become uniform. If I have something that's uniform, oh, that's related to Benford. So if my logarithm is uniform, I'm Benford. Let's look at, this is now the variance is 0.1. Does that look closer to normal? I mean, closer to uniform. Much closer. Unfortunately, it doesn't continue. So here, the variance is 0.5, and you can see major dips. What's going on? Yes, It's the scale. Look at the y-axis. So again, one of the themes of this class is to always label your axes. Think of the XKCD. The XKCD are going from 0.99990 to 1.0001. There's essentially no movement. I will risk saying this. There was a lot of excitement because gas prices fell 2 cents over the last week or two. Yes, and if you focus on what's going on in the last week or two, I'm quite happy gas prices have gone down 2 cents. If you expand your window out a little bit and look at the entire plot of what's going on, you see that gas prices have gone up significantly in the past year. So you have to always ask, what is the right scale to look at things? Well, I'm actually looking at the entire thing from 0 to 1, so the x-axis is great. Right down here, I didn't actually draw it, that would be the uniform distribution. All right, so again, if we see a product, we take logarithms, okay? If I die, I hope somebody will take a logarithm at the funeral service, just for old time's sakes, to remember me, all right? So imagine we have a bunch of random variables x1 through xn, and we want to look at their product. And I want to show that their product is Benford. So let's let wn be the product. And so what I'm going to do is I'm going to let yi be the log of xi, and I'll let vn be the log of the w's. So vn is the log of the x's. So if I expand things out, I get vn as the sum of the logs. These are just random variables. What can you tell me about that sum as n gets very, very large? It approaches a normal. Yeah, so it approaches a normal. And if it approaches a normal, and if that normal has a growing variance, then it's going to approach a normal, which when you look at it mod 1 is uniform. Oh, well, if this is converging to a uniform mod 1, then when I exponentiate, I have Benford. That means Vn should be Benford. So this is a quick proof why so many different things are Benford. If you can write your object as a product of a bunch of processes, the central limit theorem is kicking in the background. What's interesting is I actually don't need the x's to have, for instance, finite moments. I just need the log of the x's to be nice. And I'm only looking at these mod 1. So you can play this game as to what is the weakest set of conditions I need. All right, so let's talk about some applications. One of my favorites was there was a bank where an audit revealed that there was a huge spike of numbers, and they kept investigating. A lot more numbers with 4 than they expected, a lot of 4 8s, 4 9s, and eventually they traced it to one person. I will give the Seinfeld reference. Write off. What did Kramer say? Just write it off. So what was happening is somebody was having their friends sign up for credit cards and run up debts of just below 5,000. And then they would call the bank and they would report their credit card stolen, which was, oh, we're so sorry to hear that. We're going to cancel your card. We'll send you a new one. Don't worry, you're not liable for the charges. Now imagine you're at the bank and you see that there's, $17.76 in disputed charges. Are you going to investigate and try to track down who just filled up their car with a little bit of gas, which is now 2 cents cheaper than 2 weeks ago? No. What if you see that the new price, the credit card is $35,000 because somebody just bought a new car? Would you investigate that? Yes. So you need to decide at what critical point is it worthwhile to investigate. And so what they would do is anything below 5,000 was automatically just paid, and anything above 5,000 was investigated. No, it was I think a broken VCR or stereo. Maybe it was a stereo. I think it was a stereo, and that they were basically claiming that it was damaged in the mail. And just don't worry, it'll be a write-off. The insurance company will just pay for it. So the danger is when you have a hard limit like this and people know that anything below $5,000 is not going to be investigated, it opens you up to, again, I will risk saying something like this. Imagine you say that certain types of people will never be pulled over by Homeland Security for additional screening. say elderly grandmothers in wheelchairs. If you wanted to try to do something nefarious, how might you decide to disguise yourself? Elderly woman in wheelchair. Yeah. We actually don't care if you're homeless or not. That's why you're flying, looking for housing. Probably don't want to look like you're homeless. But if you know that there's a certain category that's not going to be checked, then that is, a call. She had a bunch of tea bags. I can share some stories, but not with things being recorded. So what should you do instead of saying anything below 5,000 is not investigated? Because we've just said we've created a situation where there's a huge incentive to cheat. So we could say, we would kindly ask all consumers and workers to please not cheat, embezzle, and whatnot. Okay, so we'll assume we've already done that and the embezzling and cheating is still happening. What should you do? Okay, but be more specific. Regularly audit how and whom. Okay, so maybe we still audit anything 5,000 and higher. What do we do for things below 5,000? Well, but I'm saying the whole point was there was one person who was getting a lot of people claiming to have stolen credit cards. So you need to check these cases, but you only have finitely many auditors. So you can't audit everybody.
Audit him again?
Well, but okay, but he's been sacked. It's like Monty Python and the early credits gone, yes. So one thing you could do is you could focus on the people who work at the bank and just see, are some people getting more claims of just below 5,000 than others? And maybe there's something suspicious there. So that's absolutely one good strategy. But let's look at the, we have a bunch of claims coming in between $0 and $5,000. If we audit none of them, we've just told people that this is a region where you can do your stuff and it's not going to be detected. So what should we do? Okay, randomly. So what kind of distribution do you want to put from 0 to 5,000 to determine if we audit? Do you want a uniform? So that $10, $17, $16, $19, all equally likely as a 30,000 to 200? What kind of distribution might you have? I don't think I would do a normal. Yeah, so maybe anything between 4,000 and 5,000, maybe that has an 80% chance of being audited. And maybe a 3,000 to 4,000 maybe has a 60% chance, something like that. So that the more it is, the higher it is, the closer it is to $5,000, the greater chance. And yes, you will be opening up, a window. If somebody wants to embezzle $3.14 because they like stealing things that are high, and then they'll do 2.71, next week, they will almost surely fly below the radar, but you don't really mind. That's not where you're going to take the big losses. So over here, this is a great indication of the dangers of having a fixed process where you have no chance of adjusting. All right, so the last thing, and then we will continue. Can anybody see the cat hiding in the tree or in the picture? $100. You can see it. Not bad guess because you've known me already. So how do we transmit an image? So Benford is actually used to detect image fraud, and I've done some work on this. So let's say we have an L by W grid. For each pixel, we transmit a triple red, green, blue. Okay. And so typically what we can do is we'll choose values from 0 to 255. So you have 256 possibilities. So steganography is the act of concealing a message in a message. What I can do is if I write my numbers in binary, if I change just the last digit or the last 2 digits, it's not going to change the color by that much. If I change just the last digit, that gives me 8 colors to work with. If I change the last 2, it gives me 64. Well, it's like a Crayola pen. And so where's the image? Everywhere. The entire cat is spread out And so the question is, a lot of times terrorists and other people use stuff like this to modify an image and post it. And so you're not transmitting directly from point to point. Can you somehow detect that an image has been modified to see if something good? So Benford's law has had lots of successes with stuff like this. We will continue with the theory of Benford's law on Monday. Have a great weekend.